Hello everyone, welcome to the course on microsensors and nanosensors. We are in third week and we were discussing principle of sensing, and this is our second lecture in the third week. In this series we have learned that how a simple capacitive phenomena can be used for sensing application. In previous class we had a discussion on capacitive principle, how it can be used for different sensing application, including in moisture detection, in pressure detection, in displacement sensors and all. Okay. Today let us learn about inductance. Once we know that what is inductance, we will also see that how the inductance can be changed, and if inductance can be changed, it can be measured by some mean. Okay. And that is how our sensor works, right? We have a non electrical stimuli and the sensor convert it into electrical signal. Okay. So let us see what is inductance first, and then we will see how it works and little bit physics behind it, particularly in the context of a sensor. In a simple way, we can define that this inductance as the tendency of a conductor to oppose a change in the electrical current flowing through it. Please note that we are discussing about change in the electrical current and not the electrical current. Okay. So inductance is the tendency of a conductor to oppose a change in the electrical current flowing through the conductor itself. Okay. To understand this statement, let us see this inductance, okay, where some current is flowing. If we talk about Ampere circuital law, it says that if a current I is flowing in a conductor, it generates a magnetic field around the conductor, right. So the current, this I, is flowing through this conductor and it is generating a magnetic field around it. Okay. So we know that the total magnetic flux can be calculated as a vector product of a magnetic flux density and the vector area, or B dot A, which is BA cos theta, where theta is the angle between the corresponding components. Okay. If the current changes, this magnetic flux will of course change, right. So if there is any change in the current flowing through this conductor, be its increase in the current flow or be its decrease in the current flow, there will be a corresponding change in the total flux link. Okay. Now let us recall the Faraday law of induction. Okay. By Faraday law of induction, any change in the flux through a circuit induces a electromotive force or a EMF in the circuit, which is proportional to the rate of change of the flux, or in simple term I can write E is equal to minus d phi by dt. Okay. This total flux is sometimes also written as phi subscript b. So I am using that notation. So E is equal to minus d phi by dt. Okay. Please note that I am having a negative sign over here in this equation. Okay. And this negative sign is coming from Lenz's law, right. It says that the direction of induced voltage is in the direction which opposes the change in the current which is responsible for the induction of the voltage, right. So this negative sign is coming from there. Okay. So now I have established the equation that the EMF, or sometime we call it back EMF, okay, is a negative of a d phi by dt, right. From this equation I can also say that if the number of turns is equal to capital N, I can say that the voltage is minus N d phi by dt. Okay. This equation can be reformulated in a way that is particularly useful for the sensor designers and the application engineers. So I can simply write this V as minus N d by dt of B into A. Okay. Right. Considering that theta is equal to 0. Okay. This equation indicates that voltage in a pickup circuit can be generated by varying either the magnetic field of amplitude B, or the circuit area. Please note that this area is not a vector quantity right now. Okay, I am taking the scalar component of the oriented area. Okay, so V can be written as minus n d by dt of B into A. Okay, now from this equation I can see that this induced voltage depends on a number of parameters, or this voltage can be changed by a number of means. Okay, why I am interested in that? Because what I am going to do with this inductance or this back EMF is to see that how the induced voltage can be changed, because that's what all about a sensor. Okay, if it can be changed, it can be sensed, right? So let us see some factors on which the induced voltage will depend on. Okay, the first is moving the magnetic field source like magnet, wire or coil. Okay, second is changing the current in the coil or wire that generates the magnetic field. So if I am moving the magnetic field, okay, what I am trying to do is I am trying to change the B, right? So in that case also this V will change. Second point is changing the current in the coil or wire that generates the magnetic field. We have already seen that if current I flowing through a conductor is changing, the total flux is changing, right? So moving the magnetic field source like magnets or wires will change the back EMF. Similarly, if there is a change in current in the coil that generates this field, will also result in change in the back EMF. Then third is altering the orientation of the magnetic source with respect to the pickup circuit. Okay, this will also change the field, and that's why I will have a change in the back EMF. Particularly it can affect the sign. Okay, then modifying the geometry of the pickup circuit, such as by stretching or compressing or say adjusting the number of turns in the coil, and this effect can be seen in the form of this area or N. Okay, so if I am changing either A or N, what I am doing is I am in turn changing this V. Okay, and whatever point we have seen, based on this a sensor can be designed using a inductor. Okay, now let us see it in little more detail, particularly for the sensing application with some say solenoid or say toroid. Okay, so we have already seen the Faraday's law, and you might also be knowing it from your class 12. Okay, so according to the Faraday's law, when an electric current flowing through a coil which is situated in a close proximity with another coil, an EMF will be induced in the second coil. So if I have a coil and I bring another coil which is having current flowing through it, okay, there will be a EMF induced in the second coil, right? However, the magnetic fields penetrate not only the second coil but the first coil as well. The field associated with it will also penetrate the first coil itself, right? And this is the basis of self-inductance. Okay, we'll also see mutual inductance, particularly when there is a concept of second coil. Okay, therefore the magnetic field sets the EMF in the same coil where the current has originated. Okay, so the idea is you have a coil where the current is flowing, you have brought another coil near to it. I am saying that there will be a EMF generated in coil 2, but at the same time you are also having a EMF generated in the first coil, right? And this process is known as self-induction, and the resulting voltage is called self-induced EMF or self-induced voltage. Okay, so Faraday's law for a central portion of a solenoid can be written as V equal to d by dt of N into phi B. Okay, where multiplication of N into phi gives the flux linkage. Okay, for a simple coil without a magnetic material in the vicinity, this value is proportional to current flowing through the coil, or N phi B is basically proportional to I. Okay. Now, if I want to remove this proportionality, I have to introduce one constant, and N phi B will be equal to some constant, say L into I. This L, which is equal to N phi by I, is known as the self-inductance of the coil, right? So, now recall the equation from the Faraday's law, particularly for the central portion of the solenoid, which has given me V is equal to minus d by dt of N phi B. Okay. Now, if I replace this N phi B with this equation N phi B equal to Li, I can write this V is equal to minus d by dt of Li, or since L is constant, I can write d by dt of I, right? So, from this equation, I can again define this L as L is equal to minus V by di by dt, right? This is the self-inductance in another form, okay? So, if no magnetic material is introduced in the vicinity of an inductor, the value defined by the previous equation depends only on the geometry of the device, okay, and of course the unit is Henry. So, to conclude, I have the induced voltage is proportional to the rate of change in the current through passing through the inductor. This voltage will be equal to 0 for DC because I am interested in change in the current di by dt. For DC, this component will be 0, okay. That is why I am telling that voltage will be 0 for DC. This voltage increases linearly with the current rate of change, okay. Voltage polarity is different for increased and decreased current flowing in the same direction, okay. Induced voltage is always in the direction which opposes the change in the current, right. This has come from the Lenge's law, which we have seen some time back, okay. Now, we have a little understanding of inductance, but the ultimate aim of this course is to use this inductance for sensing application. Now, we have seen that how this back EMF can be changed, or the induced voltage can be changed by doing multiple iteration, by moving the coil, by changing the current, by changing the polarity, and etc. Okay. So, in previous class we have seen that how a capacitance can be used for sensing application. Similarly, we have to see that how a inductance can be basically used for sensing application. We have introduced, if you remember, a geometry factor for capacitance. The geometry factor for parallel plate capacitor was, say, C equal to epsilon naught into geometry factor G, right? G was A by D. Similarly, we have to also introduce one geometry factor for inductance or inductors, okay. For a closely packed coil, in the inductance value can be calculated as N phi by I, okay. The number of flux linkage here is N phi equal to N into L and B into L, where N is the number of turns per unit length and L is your length, okay. A is the cross sectional area of the coil. So, if I have to write this L, I can also write N L B into A by I, right. So, say for a solenoid, if B is equal to mu naught N into I, the inductance can be written as N phi by I, or mu naught N square L into A. Please note that N is not the number of turn, it is number of turns per unit length, okay. In this equation, this L into A is very important, and this is the volume of the solenoid, okay, and this L into A is known as the geometry factor, right. So, similar to the capacitance, where we have seen the capacitance is equal to epsilon naught into geometry factor, for inductance I can write this inductance equal to mu naught N square into geometry factor, okay, where the geometry factor is nothing but the volume of the solenoid, okay, which is L into A. Okay. So therefore, having the same number of turns and changing the coil geometry, its inductance can be modulated, that makes an inductive transducer possible. Okay. Let us try to understand this with the help of a solenoid. Okay. Say I have a solenoid where the volume or say number of turns per unit length is same, but I am changing the volume of the solenoid. It is quite possible by making the coil arrangement different than the first case. Okay. The volume can be changed. If two solenoid having the same number of turns per unit length have different volume, the inductance will change, right? And therefore, sensor can be designed using this particular factor. Okay. Now, let us try to see the case where we were discussing condition of two coils. Till now we have seen condition of a single coil. Okay. So if two coils are brought near to each other and one coil conducts current, then the magnetic field interacts with the electron in the second coil and there is a induced voltage in the second coil. This induced voltage cannot be explained by the self-inductance because in the second coil there was no current flowing. Okay. To explain this, there is a concept of mutual inductance. Complete discussion on self-inductance and mutual inductance is beyond the scope of this course, but at least we will see what is this induced voltage and what is the reason behind it. Okay. So the logic behind this is the induced voltage through this mutual inductance. This V2 can be given as minus M into di1 by dt, and M is sometimes written as M21, which suggests the induction of voltage in second coil due to first, and that is what the meaning of these numbers are. So this M21 is the mutual inductance coefficient between these two coil. Okay. And M can be written as mu naught pi R square N into N, where this R, N and N have meaning explained in this figure. Okay. So for a coil placed around a toroid, for example, the mutual inductance is defined through the number of turns N1 and N2. Okay. So M can be written as mu naught N1 N2 into H, okay, where you can see H is this thickness, by 2 pi into ln B by A, okay, where B is the outer radius and A is the inner radius. So by varying the mutual inductance, a useful sensor can be designed. For example, a displacement sensor may consist of two coils, one fixed and other in motion. As the moving coil shifts its position, the induced voltage changes accordingly. Okay. So that is the concept of inductance and how a sensor can be designed using a inductance. Let us see some more example by using inductance principle or using the induced back EMF voltage. Okay. Consider a coil, okay, or consider this in horizontal position. Okay. There is some current flowing through it, okay, and this current is generating some magnetic lines. Okay. Now if there is some conductor coming in its vicinity, it can detect that because this conductor is coming in the line of force of this conductor, it will change, right? We have seen the back EMF generated is minus d phi by dt, right? So it can be simply used for detecting, say, a simple coin, for example. Okay, you can use this kind of circuit to detect any kind of magnetic material or a conductive material. Okay, of course it doesn't have to be magnetic always, a conductor can do. Okay, similarly, mutual inductance is very crucial in various sensors. We will see in more detail in coming slides. Okay, so in the next class we will see some more physical properties, particularly resistance, piezoelectric devices or principle of piezoelectric and pyroelectric. Okay, resistance is very crucial for our sensing course, and we will see many devices based on simple resistances. Okay, like chemi-resistive devices where the resistance changes when it comes in vicinity to some chemical molecule or chemical compounds. Okay, we will also see resistances for temperature sensor. Okay, we will also see resistance for tactile sensor. Okay, the resistance is simply defined as rho L by A, where your rho is resistivity, L is the wire's length, and A is your cross sectional area. Okay, we will see that this resistance can be changed by either changing this rho or changing this area or changing this L. Okay, this rho is usually the property of material. Okay, so we will focus on L and A. Again, we will, similar to inductance and capacitance, we will also define geometry factor, and we will see that if geometry factor is changing, how the resistance value is changing. Okay, and any change of course can be detected and the sensor can be calibrated against the known references. Okay, similar to that, we have to also see some piezoelectric devices, and in the last lecture we will cover the pyroelectric component, and if something else is also there, we will cover that. Okay, thank you.